Welcome back. We're continuing our discussion of verification, and in this lecture we will talk about data plane verification. In particular, we will explore how to check whether the data plane state will result in correctness problems as packets are forwarded through the network. One of the limitations of verifying the configuration is that predicting the outcome of configuration is difficult. There are various vendor-specific configuration languages, and protocols are dynamic and distributed. Prediction using configuration may also miss implementation bugs in the control plane. The vision of network verification is that we might be able to take the configuration of all these disjoint devices and figure out, given a particular packet or flow, what will happen to that packet as it traverses the network. The idea at a high level is that we want to treat each of these vendor-specific devices is simply a transformation function on a packet. Given a packet's properties, we can then determine what will happen to the packet as it traverses the network by passing it through a sequence of transformation functions. The insight here is that we can view the network as a distributed program, and we can model the packet header as a point in a high-dimensional space and all networking boxes as functions that transform that header space. So a match function might match on a bitmap and perform a particular action, such as sending to a particular output port or rewriting part of the packet header. This match and action can simply be viewed as a transformation from one set of points in the header space to a different set of points in the header space. As each router or packet forwarding element in the network can be abstracted as a set of guarded commands, the network then becomes a program, so we can use tools from programming languages to help verify the state of our network. Modeling a network in terms of header space has several steps. First, we can model a packet based on its header bits as simply a point in an L-dimensional space of zeros and ones. This is what we call the header space. In step 2, we simply model all networking boxes, such as routers and switches, as functions that transform that header space. So it may take a set of points in one part of that header space and map them to other portions of the header space. Packets in different portions of the originating header space may ultimately map to different destination header spaces. Ultimately, we can represent a router or any data plane element as a transfer function that takes a header and maps it to one or more destination headers. We say that a transfer function can potentially map to more than one tuple to allow for specific functions such as multicast or broadcast. An IP router might map different portions of IP address space to different output ports. This can be represented in our transfer function. In addition to forwarding packets out different output ports, the transfer function might also perform additional operations such as decrementing the TTL and rewriting the destination MAC address. All of these operations can be represented in the transfer function. Example actions that can be represented in the transfer function include rewriting, encapsulation, decapsulation, TTL decrement, and load balancing. A rewrite simply involves masking new bits into the packet header. Encapsulation might involve a shifting of bits in the packet header followed by a masking. Decapsulation might be a reverse of that operation. Decrementing could involve specific arithmetic operations on portions of the packet header, and load balancing might involve selecting a particular output from one of many possible output functions. We can now determine the end-to-end behavior of the network by composing these transfer functions. As an input packet represents a single point in packet header space, we can represent what a particular router does as simply a transformation of that packet to a different point in header space. As the packet traverses the network, we can represent this as a sequence or a composition of these transfer functions. So ultimately, the output is simply the originating header and port composed with a sequence of transfer functions that corresponds to the path that the packet takes through the network. Given a point in packet header space, we can invert the transfer function to tell us all possible input packets that could possibly have generated a particular output packet. This could be a useful function to apply during debugging. The third part of the header space framework is the header space set algebra, which allows us to compute header spaces that may result from the application of particular operations, such as intersection, complement, difference, or checking subsets or equality. Every region of header space can be described by a union of wildcard expressions. So our goal in applying header space algebra is to perform set operation on these wildcard expressions. If we can do that, then given any set of input packets, we can then apply a set of transfer functions to determine what might possibly happen to any particular packet or set of packets as it traverses the data plane. Applying the logic in the table shown below allows us to apply this bit-by-bit intersection. A 0 intersected with a 0 is a 0, and likewise for a 1. A 1 intersected with a 0 is the empty set, and likewise for a 0 intersected with a 1. If we have a don't care bit, then a don't care intersected with a 0 is a 0, a don't care bit intersected with a 1 is a 1, and two don't care bits that are intersected are don't care. If any result has a z in this table, then we declare the intersection to be empty. So for example, a 1 intersected with a 0 is a z, and hence the intersection between these two bit strings, or packet header spaces, is the empty set. So the header space framework is a simple abstraction that gives us a common model for all packets, and a common model for forwarding functionality for all networking boxes in the data plane, as well as a mathematical foundation that allows us to check the end-to-end properties about these networks. We can then apply this framework to answer specific questions, such as reachability. We can, for example, determine all packets that A can possibly send. This is computed as all packets that A can possibly send to box 2 through box 1, and all packets that A can possibly send to box 4 through box 1. Repeating this process gives us different header spaces that we can then apply transfer functions further along the path at box 3. Ultimately, the set of packets that can reach B is represented by the logic equation shown here. It is simply the union of the header spaces represented by the traversal of these two paths. If we invert this logic, we can then determine all packets that A can use to communicate with B. Predicates on paths can also generalize to policies. We can determine, for example, whether the data plane is free from black holes, whether or not a particular endpoint can communicate via a middle box, whether or not a path exceeds a maximum hop count, and whether or not two paths may be isolated. We can also determine whether the data plane has a loop. We can inject an all X or an all don't care test packet from every switch port in the network and follow the packet until it comes back to the port at which it was injected. If we ever see a packet return to a port on which it was injected, we know we have a loop. Of course, what we'd like to know is whether the loop is persistent. To determine whether a loop is persistent or infinite, all we need to do is determine that when the packet returns to the port at which it was injected, whether it actually ends up in the same packet header space that it was when we injected it. If the packet is in a different part of header space, then the loop may be finite. If it returns to the same portion of header space, then it is the case that the loop is infinite. To think about this concretely, we can think about cases where loops can exist in a network that are not infinite. For example, if we had an MPLS circuit that traversed the same set of physical switches, the loop may be finite if the packet returns to a switch, but returns with a different set of MPLS tags. If, on the other hand, it returns with the same tags, then we have an infinite loop. Another example of an infinite loop might occur if the packet returns to the same router with the same destination IP address. That's a case where no packet transformations are performed, and hence we know that the loop must be infinite because the same forwarding decisions will be made as were made when we injected the packet. We can also apply header space logic to network slicing. In a previous lesson, we explored how slicing a network can allow sharing of network resources between different tenants. Just as with a virtual machine, we need to ensure that no interaction occurs between these slices. Header space analysis can allow us to check this isolation. A network slice in header space analysis is simply a piece of network resources that is defined by a topology and a set of predicates on packet headers. For example, a VLAN might be an example of a slice. To check whether two slices are isolated, we need to determine that these definitions of the slice don't intersect with one another. We can do that very easily by simply looking at the header spaces defined by the injection points of each slice and the set of possible transformations that might take us from those originating header spaces to any other header space as the packet traverses the network. If those header spaces ever overlap at a particular forwarding element, then we know that the slices are not isolated. Although we focused our discussion of data plane verification on header space analysis, another tool called Veriflow performs very similar types of checks. Veriflow attempts to perform this type of verification in real time using data plane state. It monitors dynamic changes in the network, constructs a model of network behavior, and uses custom algorithms to automatically derive whether the network contains errors. Much like header space analysis, Veriflow runs its analysis over a forwarding graph and produces a set of invariant violations and a set of packets that cause the invariant to be violated. To speed up analysis, Veriflow figures out which sets of packets belong to the same equivalence classes to reduce the number of tests that need to be run. In summary, we can perform data plane verification by performing symbolic execution on packets that can tell you if the data plane state is correct. There are many limitations to data plane verification. In particular, scaling can be challenging. Another limitation is that these methods can reveal problems with the data plane state, but they won't tell you the problems in the control plane logic that actually caused the erroneous data plane state to show up there in the first place. So while these methods can determine problems, they can't tell you really how to fix them. And they can't help you write a correct control plane program in the first place. Furthermore, they only tell you whether the current snapshot of the data plane state is correct, not whether the dynamics of the control logic that might change that data plane state might ever produce an incorrect data plane state. So really we need to go back to the control plane and figure out how to verify the control plane to make sure that the types of problems that header space analysis and Veriflow can detect are never generated in the first place. Doing this with low-level configuration is extremely tricky, but the advent of higher-level SDN control languages can make it possible to perform this type of verification much more easily.